Welcome back to High Performance Computing, Advanced Scientific Computing. Today we have our practical lecture 5.1, which is Understanding MPI Communicators and Data Structures. So we have a practical lectures with lots of hands-on demonstrations where I basically connect a little bit what we learned in lecture 4 and lecture 5 in a more conceptual style, and here really put it on a supercomputer for our HPC Utin cluster. But before we go into the material of the lecture of today, let us review briefly what we learned the last time, which was really about parallel algorithms and data structures. So we shift a little bit the view of really thinking more, what is parallel algorithm? What is a parallel method? What is parallelization? So what is basically behind the idea of using more and more cores? Of course, also in a style where you would think it should have a meaning, it should have a benefit, right? We talked also in earlier lectures about a speed up. I want to achieve something in parallel, not for the sake of burning more compute cores, but for the sake of actually accelerating some computing. And the simplest kind of parallel algorithms we had was a little bit in the math area now, when we think about how you compute actually maybe the addition of these two columns here, or a matrix vector multiplication that you see here, which is a bit more complicated in the sense and this. But the idea to take away is that this colors usually entails what can be nicely parallel computed. This word nicely and embarrassingly parallel, as they called it in previous times, means that basically in order to compute this fellow here, which is the result in the end here, this gray, you basically just have to know the information that you have essentially in this part, so this column part, and then essentially, or this matrix part really, and this column part here of color. And if you do so and basically do the math, basically based on known rules, of course, here, so we don't introduce here something new, this is how we compute it, you can break this nicely into different processes that actually then, according to this color code that you have here, can actually compute this in parallel without any meaning or any need to really exchange information. Of course, at the end, the result should be somehow captured in this vector here. But in the end, we don't, need any message exchanges between this kind of simple algorithm. But we also learned already in some of the other applications that, of course, as soon as you get to more, let's say, sophisticated simulations, like we always discuss a little bit the ocean, that will be one part of your assignment too, right? When you have wave propagations and so on, you directly need your neighborhood information about the wave height, maybe the wave height as one example or so. And with this, we are directly in the MPI communication, and that's what you already learned, this broadcast, and you also learned send and receive. So the last, basically also the last lecture really introduced a little bit this non-blocking communication. And this was a little bit interesting to see, especially if you know the material of lecture 3 only, and the previous ones, which are always kind of a blocking send and receive. We can also introduce non-blocking messages, like here, the MPI receive and MPI send. That's what you already know. But of course, what we also can do is to have this kind of non-blocking receive and then basically have a blocking send. But in order to basically synchronize between them, you also have to introduce a certain kind of synchronization statement. And we had MPI barrier, we had MPI wait, we had several of those. But here the wait is something I will also demonstrate today, that of course this non-blocking communication needs to synchronize. And one idea that was a question from one student, I think, in the class, who said why we want to synchronize and wait, because basically every core can go ahead, compute faster, can already work on the next data item, can already proceed. Why we wait? Because this waiting time is of course a performance bottleneck here that we actually will review in our performance analysis lecture later in this course. But the key message to take away is that really these simulations, now think about the propagation of the ocean, they have this kind of idea that every time step I do some message exchanges. And we will review this today, also with HPDB scan and other algorithms. But think about what I see here. Here you see the Cartesian communicator that we also introduced last time. And think about it that the wave is propagating, and you need essentially in every time step, essentially the information maybe from the neighbors, right? To compute perhaps the wave height, and then you propagate the wave height in your tile to all the others in order that they can actually compute the wave height in the next time step. So in other words, you need the synchronization at some point in time, because this constitutes one time interval. And what the time interval is and how it reflects real life is, of course, a different issue. But in the end, you have to see you need the synchronization to start the time step in the next iteration completely accurately. Because if you have, let's say, 1 or 2 cores in this, let's say, ocean that you have at 3 times 4, and then one core is just very hectically already, let's say, in the computing the wave height in the next 3 time zones, while the others around are very slow because there's maybe a boat on it, here's a lighthouse, there's some rocky stones, more computing needs to be done, more physics. And here this happily rank 6 is, getting ahead. Of course, it will be inaccurate for each time step. You can't do this because here, this fellow, even if he is super fast, is dependent for the next time step to compute on its neighbors in order to calculate the wave height really correctly. And this is connecting a little bit to what I already introduced with the heat in the room, with the stencil methods. It's the same point. If you have the heat in the room, and let's say one part of the room is very hectically getting ahead because being much more faster than all other cores, it doesn't help to really compute the physics at that time step, because the core or this process is dependent on the neighbors. And this says it a little bit why we often use the synchronization statements. And of course, performance issues is another issue in this, what we also will review in more lectures later. We also then basically had this example that I also put into light. So basically show you some hands-on experience with this non-blocking communication, but obviously this will be also part of your assignment. So then with hands-on in your own, let's say, login and so on, that will be coming much more into play. We also learned then a little bit that parallel algorithms need some sort of data structures which support the parallelization and the message exchanges. And we basically learned about the simple MPI data types like MPIint already. So I can, of course, transfer an integer. I can transfer an MPI char. This is not a surprise to you. Basically, the simple normal programming language variables types are, of course, kind of copied in the MPI world. But we also learned, because we do message exchanges a lot, sometimes it just makes sense to combine those in one message exchange. Or if you think about the buffer perspective, and this is something we will allude to much more today, the memory layout that matters here, maybe we can even simplify certain aspects of this. And this brought us to the derived MPI data types, where you can create your own derived MPI data types from these simple MPI data types that we know with MPIint and char. And you see how this could work in 3 examples here with a contiguous vector and indexed, where essentially we will review this significantly with some examples now in practical lecture 5.1. But you see contiguous memory space, which basically means this word. You have just 3 types from some simple old type that you generate for a new type. So you can basically have 3 different types summarized as one type. Then we have this vector type, which gives us perhaps 5 items here. And they're basically always 2 times long, or the block is really 2 times long. And then you have the so-called stride that tells us, okay, on what memory position I should put them. And here you have the stride of 3, that meaning here is always a hole. And then we learned, of course, there's a much more complex element to it, which is the indexed, where you have, let's say, almost full flexibility how you put essentially the memory space to the data structure, where you have different blocks here, even of different sizes. You see here 2 block and a 3 block or 1 block. And then the displacements, where you can actually put exactly each of the values to say position number 2, position number 9, position number 12, and so on and so on. So, but in the end, I think this becomes much more important to review in our use case when we work on it. And I brought you some interesting use cases out of practice where we want to have maybe certain elements out of a matrix, just a triangle, or maybe even just a column extracted from a big matrix. And of course, I don't want to do this manually. If you think about your use 1,000 cores and you distribute it very broadly, a very big matrix, you don't want to end up and make the indexes yourself. So you have a certain idea of using a derived MPI data type for that. And then towards the end of the lecture today, I will introduce you a little bit already to something what we learned about parallel I/O. So you know there's a parallel file system which usually supports concurrent access to files, and that helps us for many different things. And of course, will be used in the second part of the course really intensively when we look at all the different application areas. But I introduce you already a little bit the look and feel of a binary file format called hierarchical data format. So binary file formats obviously are a very beneficial part for us because we don't have to transform it. You know, the computer is computing in binary, so why we should lose time to basically store it to disk and then just that people can read it. We talk about a library that is used in wide areas of sciences, really. And here we will just pick some of the earth sciences, a reconstruction on a city based on laser scans, which brings us a so-called point cloud, which doesn't look like a city overall, but once you do the clustering, which is one of the machine learning / data mining methods, you see the DB scan that I will show you today a little bit, we will reconstruct the city based then on this, let's say, HDF5 format. And there are some interesting takeaway messages about it. This is more the message exchanges, right? Then the hierarchical data format is really something which you drop to disk. And with this, of course, we will have some interesting demos. So fasten your seatbelt for a very practical lecture today. Let's go. Of course, it's an additional lecture really fostering what we learned before in Parallelization Fundamentals, Advanced MPI Techniques, and the parallel algorithms and data structures. So with this, we really will learn about non-blocking communications. The Cartesian communicator will be really explained with 2 more examples. And of course, while doing this, it should be, especially with the non-blocking communication, Cartesian communicators, much more easier to understand by having, let's say, real-time demos. Obviously, they are, of course, related to your assignment. So you will play around with these constructs a little bit and modify one of the examples I will give you. And of course, I give you some application examples on Newton for that. Then, while this is more the communication part of data structures, and so on, maybe we learned that, of course, the first part is to maybe, instead of sending a couple of times an integer over the wire, again, in every single individual message exchange, maybe it's more smarter to combine a couple of integers and then send them just once. And I think with this message exchanges, you're directly at this MPI derived data types, which the second part is about. Where we learn a little bit why this is useful. And I have some interesting application examples for you, of course, also what we do on the Newton system. And then we talk a little bit about the MPI-IO and parallel file system approach of HDF5, which we already conceptually established, which being more or less in HDF5 point of view, a file system in a file system. So you can have very nice structures in HDF5, and we'll also give you a demo there which reflects to basically our HBDB scan algorithm that one of my PhD students developed many years ago and is probably still, if not basically today, really the most scalable and parallel HBDB scan algorithm you can have. So there are many parallel DB scan algorithms, but I think still this is one that scales best. So if you know differently, please contact me. It would be quite interesting to really collaborate maybe in this area. With this, you really understand binary file formats, HDF5, and basically then also using this interesting H5 dump tool, which gives us a little bit of view inside a binary file format. You are basically in a space where more doesn't help you anymore. You cannot just more and then any HDF5 file and look into it because it's binary. So we have to have specific tools to look into this, and I will show you when we do the demo, basically with an interesting point cloud data set from a German city called Bremen on this Newton system. So the learning aspects are really manifold here. I put a highlight here on parallel programming. I mean, IO, non-blocking communication, Cartesian communicators, and how they actually reflect then scheduling issues for the Cartesian communicator, where you have to have the right amount of cores being available. This is something which is really a key for parallel programming. And also the HPC environment tools, HDF5 dump tool is just one of them of many that we will learn. And in a way, by learning again on this HDF5 and the idea how it's used, for instance, in the HPDB scan, but also then the derived data types, this is really a foundation of approaches where you can immediately start and help scientific domain scientists to really program in parallel. So a very interesting lecture, and we start here now with non-blocking communications and communicator examples. Because we have a practical lecture, I will go through these slides a little bit quicker, as you know, basically we had already this material in lecture 5 and lecture 4. Now we want to see practice. So I will be here very quick, but of course, people that just hit this YouTube video here, please be referred to lecture 5 and lecture 4, where I explain some of these aspects much more in detail. So we talked about this non-blocking and blocking communication, and I think it's time to go and so a little bit about practice here. So essentially what you see here is already that I'm logged into Jotun. So you have this Jotun cluster that we already know from basically previous lectures. And I will start with basically going in our HPC course directory, and then have here, of course, within MPI, certain couple of elements really that we will do today. We start, of course, with the non-blocking, as I suggested, and clear here a little bit and look what we have. So, of course, we have a non-block example in C and a submit script. So basically, let's look a little bit what the source is actually looking like in this non-block example. And as all practical lectures, of course, you have that same materials, more or less what I describe here in the slides, so that you also can follow there. So you have a typical MPI application. By now, I don't have to explain much more about this. I hope is com size and com rank. But depending on the rank, of course, I've now basically two roles, right? You remember the rank can be used because it's unique as different roles. So let's assume that we want to send something. And you see here, we are using the send buffers in a certain buffer size. It's not so important. But what I want to do is to get basically the processor name here, which is maybe interesting for you also to know that we can do this. Another interesting tool in the MPI environment to really understand on which core it was really running. And then you see a little bit here, this funny message. You say, because I'm task 0, so to speak, I say, hey, task 1, etc., please don't set managers, set money, and so on. So here we do basically this task 0 sending a message with a char and this message to the other processor. And of course, we see here a little bit a certain tag and so on, and we do this in the MPI com world. What we get out is an MPI request. We didn't really talk about very much yet, but this can be incredibly useful to get information out. And you see also that this is a request to the MPI engine, so to speak, of performing an, let's say, non-blocking send. So we want to understand if this send was received at some point in time. And we can do this by MPI wait and use this request essentially of this message exchange and wait here. You see here, we are relaxing a little bit before that. And once this has been successful, we get a so-called MPI status, which is also incredibly useful because then we can essentially thinking about that, that we have essentially, getting lots of meta information about the MPI execution. Now, when this is the sender, and you see here some small part where we have this MPI request null, meaning that it's probably done, or basically that actually the request is still moving around. But the second role is, of course, obviously now the counterpart of it. And you remember for every send, there needs to be a receive. So here we do a non-blocking receive. And the same idea goes, of course, that we basically have this get processor here name, where we would have the receive buffer. Obviously, that will be filled from the send buffer over the wire to the receive buffer. And essentially here we have this hello there user. I've just started this receive. And here we have the same counterpart now to wait for essentially that there was someone sending something. So here you have the receive request we're waiting for in the wait. And of course, obviously, this is executed completely in parallel with two processors, ideally here. It's a quick example, all this. And one part will be this part, the upper part, and the other process will execute this part because of this if rank. So obviously, if you have done this, we want to have some information out, the receive request, the lingers, and so on. And by this, we want to have some meta information out there. As I told you, we can use basically the status quite nicely to get meta information out. So how many, let's say, chars were really going over the wire here, right, for MPI char, and we can have this in this count variable that we then just print out. And of course, we want to see what the message was. But I think the idea of this MPI application is pretty clear. Let's go to now, do the same drill we already know very much, module load, GNU and OpenMPI maybe. And then, although we have the executable here already with a non-block example, you don't really have to do this here. But let's assume we don't have this, this already. We have the C code that we want to have this -o named as non-block example. And yes, here's some warnings, which is a good idea sometimes to look at here, because it's not a beautiful MPI implication and not perfect. It just should show you a little bit what non-blocking communication and the MPI wait system means. So you can ignore this in this particular example. More importantly, what's more important for us, of course, is how we submit it to the cluster. And by now, you also know that drill a lot, I guess. So basically, you have the same with module load GNU and OpenMPI. You make sure you have the right link to the executable here, which is our non-block example that has been just compiled. And then we do an MPIRun, of course, with two cores here, creating two processes where one is taking rank 0 and rank 1. And you see already that we connect here to the beginning of the lecture again, the first, practical lecture 3.1, where we did exactly the same thing all the time. So you see also with the assignment 1, I think, which everybody of you has now submitted, you already know it's almost always the same processes, kind of the stepwise walkthrough. You basically have a text file, you have the C program out of this, and you compile it and do the job script, and then of course you submit the job script. So by doing so, we want to check if that is really running. And of course, it's a very simple program. So it will be C for completed in the status here very quickly, which in other words means we should have here also an output file any moment, which is basically reflecting here the output. So let's see what Slurm has as an output here in this particular example, where we go in and here, it's basically now what we had in the C program. Hello there, user. I've started to send this. Now he was this relaxing, having this Iceland sent. And then we can already see, okay, there's something coming out. And basically, you see also it's not really deterministic. It's clear because it's executed in parallel, but the output is kind of, accessed by both at the same time, alluding already to the problems why we need this parallel I/O in the first place. Which I explain in part 2 of the lecture much more. But you see, it obviously was running. We got 130 characters, and if you have time enough, you can actually count and see if that's really true. But in the end, we believe that here there was really something going over the wire. And that is the idea now of a non-blocking application, admittedly very, very trivial, but still captures the essence how you do non-blocking communication with essentially the idea of the MPI wait. And there will be more examples of that later indirectly, because we of course use non-blocking applications and of course also examples later in this lecture. So in a way, that's all here as usual already on the slide, right? And we could use these later also in basically different interesting parts where we do this maybe 4 times to do this, non-blocking communication with all neighbors here. That will be something we will look later on, where you can imagine this has incredibly useful applications in parallel algorithms, especially if you combine it, for instance, with a Cartesian communicator. So we learned about the I receive, I send as examples, MPI wait, perhaps also important for you is the MPI, W time here, that is elapsed time per processor. And there are much more of them in the MPI specification, but these are quite ones that are very, important. And of course, think about that. Usually when you do some elements of this, be careful. Performance can be, let's say, hampered here and there. Optimization pattern is, for instance, that of course it makes no sense to do an MPI I send and MPI wait, as I was just saying, or basically describing to you. Then you couldn't just use the MPI send, of course, right? Because you block directly. But if you do, let's say, something in between that time and can use the time productively, then there's, of course, a different issue. And we will learn on this basically in lecture 8. So I think not overdo it in this lecture. We had this non-blocking communication example in detail already described here. You have the description again. Basically, a little bit here in the yellow blocks. It's important to understand this really, because this shows the essence of non-blocking communication really. And we have done this, we have executed this, as you already know, with the compiling part in it of the C program, and then we submitted it here, but you see also in this slide, of course, with 2 cores. So no secret, not much news, except that it's of course now non-blocking communication, not only a send and receive anymore, it's an I send and an I receive. Still very similar to what we did before. We also learned before our MPI Cartesian communicator, and we learned that it's a very powerful tool, and that of course MPI enables us to really create groups of different communicators. That's what we will also do in later parts actually of here this course. But the Cartesian, of course, had a very interesting structure that comes with it. I'm suggesting already the name of the MPI Cartesian communicator, where you have a Cartesian grid over some space. So this enables us a lot for applications to have, let's say, a kind of a logical array around it that you basically can model and start using for getting, for instance, this ocean simulated, right? You have a relatively systematic way. Each of those still get a rank, as we learned, right? Here was one example of this, how it conceptually now looks in, where you have the rank information. And, when you want to send something to the neighbors, as suggested here, of course, you have to know where you basically want to send information and where you receive information from, right? So this is, of course, here, these two, basically the source is here from 8, you receive something, and to 4, you would like to send something, if it is, of course, in this direction. So the direction actually, of course, matters. And you could imagine that, of course, I can do the same in this part here. And of course, now think about that. I want to have the wave height as an example. How many times I would do it? Basically, every one of these has to do it in this time step. And then I have the next time step. So I have to synchronize that all of those are finished. And then I go to the next time step, next time step, next time step. So this really alludes to something we call MPI shifts, and then basically learning a little bit that, of course, the MPI shifts, as I said the last time, are actually not really shifting. It's one of the most misunderstandings, perhaps, in the MPI Cartesian communicator learned on my experience with students. Always think about that the shift is preparing the communication. The real communication, as we learned, is done still by the MPI send receive, or maybe also the non-blocking ones. Very important to understand, because here, of course, we have a new idea of getting coordinates. If you remember, we have new ranks in the system. We still have in our MPI com world the old ranks, but in this 2D communicator, we of course have here new ranks that are arranged in this particular communicator in order to make the message exchanges happening. So with this, we basically have a very simple illustration here that I want to just demonstrate also. So let's go to more practicals in this example. So we enter the Cartesian world here in this example. No. Yeah. So CD Cartesian. Again, let us go quickly to basically the C code, which is nothing else. And I have just explained in the idea of the slide. So we do basically a creation of a new MPI Cartesian communicator in a 2D world. It would have the dimensions of 3 × 4, as we have seen on the slides. And then there's the interesting part of periodic, saying essentially this aspect that I've shown in this slide. Do I want to stop here? Or would I say, you know, if this wants to propagate information here, should it start at the beginning here on the top? So there's a certain idea of saying periodic, right? If you want to do periodic message exchanges again and again over the space. And of course, the same is true in both directions. That's why we have to specify it twice in this particular source code. And then there's basically this creation of this Cartesian communicator. We see as the ampersand. And so in this Com2D now is our new communicator, which is a different communicator now from MPI Com World. It is this 2D Cartesian communicator. And here we basically say what we want to have. We want to have the coordinates that we have to use. And with this rank, we basically give, of course, a unique idea now that basically everybody has a different rank in this particular Cartesian communicator, which is now, of course, for us very interesting to think about. So we want to know then, of course, what are my coordinates in this particular rank and so on. But we also want to do some small message exchange. That means we have to understand when I do a certain direction of a shift that you basically have indicated here, how basically should I know where my neighbors are? You see here, we create the dimensions, we create the communicator, but nowhere in the world we directly know so far what are my neighbors, right? In other words, how should I know if I'm, process rank 4, that, my neighbor is basically 5 and maybe 7 on the other side and 0 and 8. And this is beautiful because MPI helps us here in basically using now the shifts and understanding where I should send the message to do the shifts. And let's assume we want to just have A here as a rank for information and B as another integer that I want to, work with. We basically do the send and receive based on this information on the source and destination. And you can imagine, because this is now executed many times, right? Let's assume we do this 3 × 4, 12 times. Then you basically can understand that, of course, we get 12 times this output, where we say always the source is basically and the destination is, so that we have a little bit a kind of message exchange here. And I think the best explanation is then if we execute it. So we need a submission script, as you already know for this. There's no surprise here. This time we want to have not 2 processes, but 12. So that's interesting. 3 × 4 = 12. And this will be an important part as I demonstrate you later, and make sure you have the card example there. For simplicity, I will not compile it here. I think you can imagine it's the same steps, MPI CC card example, to save some time here to demonstrate you much more other parts. We fetch this submit example. And of course, because it's a very trivial example, it's almost directly completed already. So we assume now that each of these different outputs that we will have has a certain number of message exchanges shown and the output of it, but of course based on different ranks. So you see also the IO every now and then takes a bit of time. And now we have here our 29 process from the end here already as an output. So let's look at this. And of course, you can see here for each of the rank, because it was now executed 12 times. So from rank 0 to rank 11, we have this information where I've sent to and what my coordinates are in this more Cartesian space, right? Which is again, then basically this part of information you see here in the middle. What is the row and the column in the Cartesian space, but still having, of course, also the rank information available. So that is the simplest, let's say, idea here of making very short send to destination with people I don't really know. And, this is the interesting thing. People process around as a neighborhood. So that's the interesting part, that MPI knows that. and provides us with the information, the coordinates, so it keeps track where we are, and also enables us to understand when we send around us how we address them in order to get the destinations. Of course, this is a very powerful part. And I should also say, of course, you have seen, because we have this Cartesian setup, now we have to think about that the number of processes that you assign to them would also, or should also, make sense. Right now you have a 3 times 4 grid. And when I execute this now with 11, I think many of you can basically understand that this will not fit, right? In a way, at 12 grid cells in the Cartesian, but 12 processes. So what's happening then? So we execute again as batched. Wait a bit in our job status. Of course, it's already quickly completed, our number 30 of the job here. So let's wait until there's an output. And we assume that there should have been some trouble running this. And you can already see already on the byte size here a little bit that there was some different output. And you see also that here that this really doesn't work. You have to be basically careful when you have the job specified, and actually then also, using a communicator, you basically have to have this job specification with the number of cores matching the communicator. So let's correct this rather quickly so that we not run again in this problem, just to show you, of course, that this is essentially important. And of course, as a practical lecture, this is all what we had partly before with the Cartesian in the last lecture. I explained that. Now you see how this comes to life, but also the Cartesian will be part of your assignment, number 2. So basically you will have your own hands-on experience, which really foster the learning experience, how the non-blocking communication even works with the Cartesian together. Here, now just quickly, the idea of this periodicity again. So periodic, false and true, you can imagine you can combine this, always having this communication in this direction or this direction. But important to say that there's a next time step where I can have, let's say, someone working, which means a periodic here, and I can do this in these different directions. And of course, this also reflects what we said, that of course the direction matters, where you want to have send and receives. Maybe one direction you see here, it could be the wave propagation in this particular direction. But of course, thinking about what we discussed earlier, that maybe your neighbors need to have, the kind of information exchange about yourself, and you also dependent on the neighbors, we maybe want to have a much more elaborate setup of message exchanges, not only propagate forward, as we see here, a little bit like the wave forward, but also before maybe exchanging neighborhood information about the wave height to calculate my own wave height, because I'm dependent on the tiles around me. So in other words, there's idea then of propagate of course a wave over all these tiles. And when I said about essentially the shifts, of course there's some certain positive shifts, negative shifts that you can directly imagine. With this, I can steer the direction of the waves depending on the wind or so. It really doesn't matter. It's an application specific problem, but also means that with a periodic you don't have any problems, while with a non-periodic we can imagine the waves at some point in time at the end of the Cartesian grid, which gives us then an indicator. We call it a dummy processor, really, with MPI proc null, that then, of course, says, well, you reach the end of the grid and there's nothing more to be done. But in the periodic, you basically, of course, go then back, as we just learned, on the other side again. And this was a little bit the example about this, basically a very simple example. We have executed it on 12. We learned by putting 11. It's not really a very good matching part. And it's basically something where, we have crafted a very simple output and had done one shift. Okay, so I think this is a very trivial example, but still, it captures the essence. And now what I said also to you is we want to have maybe the information of the neighbors. So here's a source code that will be one of the foundations for your assignment that you have to add a little bit to in order to understand, how we work in parallel. So I will demonstrate that example also. You see here already with the neighbors, up, down, left, right, we already thinking about exchanging with our neighbors informations and not anymore in one direction. So we really want to have all our neighbors kind of, known. So you know already I can actually get this with a Cartesian shift of understanding up and down and left and right, my neighbors in this certain array that you see here, right? It has different positions based on this. So it's more for simplicity, essentially, to do this up, down, left, right, that we understand the neighbor situation. Of course, officially it's here more or less 0 to 3 in an array. And here we do maybe a 4x4 dimension of this particular array. And of course, now when I want to do this, we have learned that this is just preparing the information of the neighbors. And I give here something out which says, okay, these are my neighbors, but still you need to do some MPI communication operations still, right? So of course, there's something following, which means I do the non-blocking communication 4 times, and then basically with a send and receive. In other words, we have 8 requests from MPI, 4 times receive to all neighbors, 4 times sending to all neighbors, and then 4 times receiving from all neighbors. So in a way, we have 8 requests, and we say, before we enter the next time step in this wave propagation, maybe example, you would say, I have to wait. Otherwise, the physics I compute will be wrong. So that's why basically you have this wait all for all 8 requests in this MPI status. And only if these message exchanges have been successful, I can continue. And usually that would mean I have a bigger loop here that says, okay, next time step. And this would be the learning experience in your assignment 2, which is actually worth 20%, not 10%. It will be a little bit more elaborate, but also not starting from scratch. You will modify this example that I now demonstrate. So let's go to this more elaborate example of this Cartesian 2D. And of course, the source code will be available to you. And the assignment will describe a little bit how to change this. So let's look in this Cart2D.C. I have already explained it. Basically, you see the for loop 4 times. I will do this, send and receive. So I'm reading to MPI request in the number of 8 here that I wait for. And in a normal application, you would say now, okay, I will have a bigger loop around this to basically encapsulate or model really the time steps. So let's run that example here. We're coming to the end also of this lecture, part 1, but we have a submit script, of course. There's no surprise. Instead of 12, we have 16 processors now that we want to use. So let's S-batch this, and basically what we want to achieve with this is that we now have not anymore one shift there. Basically, we have the shifts with all the neighbors, so I will receive information from them, but I also send information to them. And as this, of course, now is 16 times executed, right? That means there should be much more output for all of these different processes coming. So let's wait. It should be completed already, the job. You see that here, and it's a 31 job. So let's aim of doing the 31 here. And here we can now see we have the 0 to rank 15, so 16 processes, and they already define, have special coordinates, of course, in the Cartesian, but also define nicely here, what are my neighbors up, down, left, right. And as this, of course, is for every rank differently, you see here the numbers varies, and we can see that this has actually worked. And in this way, of course, you also can exchange different information, not what you received here, that you basically just send around then the neighbors. You can exchange now the wave height. And you have suddenly, from all your neighbors, calculated the wave height. That helps you a little bit to calculate your own wave height in this time step. All right, so as I said, in the practical example and the assignment that you will do in the course, you will exactly work a little bit with this to foster the understanding of the Cartesian communicator. And in part 2, basically, of our practical lecture, we will learn then much more about MPI derived data types and parallel I/O. See you then.